we are very pleased to have Toshi Nishimura and Alan Dyer here, who are co-authors on a recent paper. I'm trying to get I have the title of the paper, Fine Scale Structures of Steve Revealed by 4K Imaging. And of course, we still are fans of Steve and the eclipse and all the things here. And this is similar. Well, I don't know if it's the same as your AGU presentation, but I thought your AGU presentation on this topic was great, and very glad to have Alan here as well, talking perhaps about taking these photographs more in a scientific style, perhaps, or anything you want to share about that and the paper as well. So thank you so much, Toshi from Boston University.
No, thank you, Lisa and Laura, for inviting us. It was also nice to hear all the group stories as well, by the way. So this is a joint presentation with Alan and myself. We have recently done research with Steve about fine scale structures that exist along this homogeneous looking Steve arc. So that's the thing we'd like to spend some time on and discuss here. So just to introduce my involvement in citizen science, I was the co-author of this McDonald's Science Advance paper on Steve, and before that I had no citizen scientist research in my career, but through that work with Liz, I was really convinced that the citizen scientist photographs and videos are really powerful for doing scientific research. So since then, we have done a number of collaborations with citizen scientists, Rocky Rabel, Thomas Spence, Alan Dyer, and other colleagues in Europe who had amazing photographs of Steve and other proton aurora imaging. So those imaging were there when scientific instruments were not available. So they become critical piece of research for unveiling important structure of Steve, and they really help us identify magnetospheric structure of Steve in these two researches. For this one, the cause of the simultaneous occurrence of green and red emission in the subarray ionosphere. So we're really thankful to the citizen scientists' contribution for enabling this research. So then jumping onto the Steve events that we're looking at, I'll let Alan talk about this move in a moment. But just to give an introduction, so back a little less than 2 years ago, Alan sent me a message saying, "Hey, I took some nice videos of Steve. Take a look." And that included 4K video of Steve. I've never seen that kind of thing before. And that really amazed me and changed our ideas about Steve a lot. And so that's a basic idea of this research. So that Alan's videos are really the driver of this research. So, so I have two slides showing Alan's videos. One is all sky, the other one is 4K. So we'll hear from Alan about the story behind. Okay, so back here. Okay. Please go ahead.
Thank you, Toshi. Yeah, it was. This is really almost maybe the last time I got a good chance to shoot Steve, and I was shooting with 4 cameras this night. I think Steve had already begun to appear. And so, but there was an active aurora this night, and it was just the kind of conditions, a KP5 level aurora, where you think Steve is ripe for appearing, and certainly he did. And so I set up the time-lapse camera with a fisheye lens, which I purchased really specifically to do this, and to catch the evolution of Steve. But I was also shooting with another camera, which we'll show probably in a moment, for the real-time video. And that was the first time I'd used video to shoot Steve, just to see what it would capture. And it indeed did capture more detail and structures than we knew really existed with Steve. Because in the past, of course, as amateur astronomers and astrophotographers, we're shooting exposures of a few seconds long to minimize the noise and capture the most overall detail, but it's blurring the fine structure and detail. And I think that's the lesson that I've learned from this night, and that I include in my talks, like to the Aurora Summit last November, where I talked about to a room full of Aurora fans, what you can do to maximize the scientific gain from your images. And you may have to sacrifice the beauty shots and go for shorter exposures, means shooting at a very higher ISO speed to capture the very fine time scale and not to blur the fine structures with very short exposures, which requires shooting at higher ISO speeds than we might normally, so noisier images. Or in the case of the movie, to shoot real-time movies means shooting at very high ISOs, 25,000, 50,000, something like that, and a very fast lens. And that was the first time I tried that, just to see what it would do with the Canon R6, which is capable. Not all cameras are capable of doing low light video like that, but the full frame cameras with the lower megapixel count generally work pretty well. But coupled with a very fast lens. I was using a 21 millimeter f1.5, I think it is, wide open. That's key as well. And just shooting real-time video, 4K video. And that's what I captured and sent to Toshi and said, is this of interest? And it certainly was, because it captured that very fine structure. And so to capture images and movies for science generally requires, I think, a couple of things that I'm sort of focusing on is short exposures, if not real-time movies or rapid cadence time lapses, to capture high time resolution and fine spatial resolution in the structures, but also trying to set up a camera like this with a very wide angle lens and trying to do it as soon as possible in the night before Steve appears, when there might be a red SAR arc, perhaps, and to capture that holy grail of the red SAR arc evolving into Steve. And I've yet to do that, and because it may or may not happen. But to try to capture a full sequence of Steve with the wide angle lens, so now going for a very wide view to capture the big picture of the evolution of an arc like this and what it changes into and from as it evolves over time. And here you see Steve kind of appearing, but I caught it, kind of at its peak, didn't capture the beginning, but then you see it drifting off to the south as well. And the green picket fence fingers appearing just briefly here as well. And so those are the two kind of things that I'm focusing on, is the wide angle time lapse, but also the high spatial resolution and time resolution shots taken with time lapse cameras or real-time movies to kind of capture more information of use to science. And that's what I kind of promote to people. If they want to shoot this, yeah, you can get the beauty shots, but for science, you may need to sacrifice some of the beauty elements and go for noisier but still valuable images. So that's what I preach now in my talks, and trying to do when we have the opportunity, and we haven't had for a while with Steve lately. So there's the real-time movie with the Canon R6. You can see a couple of satellites going by, and it's noisy, but it's got detail and structure, and it shows you those fine structures, vertical, whatever they are, that Toshi wrote about, and Eric and the like, and showing that flowing structure, which in an exposure anything longer than half a second or something, you just blur right out. This is 30th of a second real-time video, so you're really getting fine time resolution on it. And still with a reasonably wide angle lens, because it's real fast, but this probably could have benefited from, this was a 21 millimeter lens, could have benefited from a 35 or even 50 millimeter lens, what you would not think to shoot an Aurora or a Steve with, but it would zoom in even more, and many of those lenses would be very fast, f1.4, there's even f9.9 or 0.9 35 millimeter lenses, which would be superb. Maybe not the sharpest optically, but that's not really that important here. You just want to get the speed to keep the shutter speed as fast as possible and the ISO down as low as you can go, so it's not as noisy as it might be otherwise. But you really can capture the fine structure in real-time movies that way as well. So keep that in mind for those of us that have the cameras capable of doing low light movies like this, like the Canon R6, the Nikon Z6 models, the Sony A7 or the A7S series are particularly good at doing this low light video.
Yeah, it's really incredible to see the satellites moving through there as well. You have some clips with the picket fence also, right? With the real-time video, or I-
On this display, I can't remember. Certainly in previous displays I did. In fact, I think the one where you were in Calgary, Elizabeth, this is time lapse. This is not real-time video. This is time lapse of, but again, quite short exposures, rapid fire. But this is not real-time video. But I have shot Steve or the picket fence with real-time video. And again, I think it was May, I forget, 2018, 2019, one of the times you were here in Calgary for an Aurora colloquium, and Steve appeared on cue for you.
yeah, yeah.
Yeah, so this particular video doesn't have no picket fence in it, but
No.
the 4K video by Justin Anderson had a picket fence in it, and they do show some fine scale, very rapid motion that we can't typically see in regular photographs. So they also show something that we scientists don't understand. So we should look more in detail. Well, in any case, in this research, this purple or grayish Steve arc is the main scientific interest, and I've just rotated the data so that Steve is kind of aligned with the pixel lines, because we are interested in seeing quantifying these small scale structures of Steve. And the great thing for this event, really thankful to Alan, was that this, Steve was taken, when the Steve was nearly overhead. Overhead in this case means pretty close to magnetic zenith. So the magnetic field at this position, Talent backyard, was pointing within this pixel. So all these vertical structures are pretty much, seen on this skinny arc over here. So the structures we see here are pretty much horizontal. If we are away from the zenith, we see a projection of vertical structure. So it's really hard to talk about the spatial structure of Steve. But thankfully, in this case, we can pretty much focus on the horizontal structure. So this really amazed me, and we can really see the true structure of Steve that we couldn't really see. The previous perception was that Steve was just a homogeneous arc, or arc with just large-scale structures, but that was not really correct. We need to understand the physics of Steve. We need to really quantify the scale size. That may really affect the chemical reaction that is responsible for the mission. So yeah, so those are the things that we have done. To quantify the structures, we need to make some sort of slice. So in this case, we have sliced the data along this pixel line and plotted as a function of distance. And then we have split into 3 color channels, red, green, and blue, to see what kind of propagation structure we see. So the blobs we saw propagating along the arc are these transient luminosity enhancements. They are propagating from bottom to top. That means from east to west. The slope tells us the propagation speed. The distance between the enhanced luminosity can tell us the wavelengths. The separation at a certain time can tell us, so this is the wavelength, and the horizontal separation here is the wave period. So those are the ways we can use to quantify the wave properties of these fine-scale structures. Another point to make is that there's no clear difference between the color channels. So that means that these are really whitish or purplish emission, not that particular spectral line, but all the colors are responding at the same time. So these are internal Steve structures, not something like auroral emissions. Okay, another important thing is that over large spatial and temporal scales, they appear to move just quasi-periodically, stable waves. But if you zoom in, and that's really not the case. For example, this structure moves a little slower than the next one, so they two are kind of merging at this point. So they propagate at the different speeds. And one structure decays and a new one forms on the sides. So it's a the active generation and dissipation of the small scale structures. So they are not stable waves propagating at a certain speed, but some active generation and decay processes are going on within just tens of kilometers of scale size. So like I said, we can quantify velocity, wavelengths, and period by just looking at the spacing between the emissions. So we have traced luminosity structures. These lines trace the peaks of emissions. So the slope tells us the velocity. The Steve is known to be associated with fast plasma streams along the arc, but the speed is not constant. It goes up and down between 8 and 10 kilometers per second. So it's a pretty substantial variation of the plasma flow. The wavelength, meaning spacing between the lines, is changing also quite a bit. So there's a wave period. So what we can learn from here is that it's not very correct to think that there's a uniform plasma flow that is heating the atmosphere. It's more like wavy or small scale flow structures that are changing within a few seconds of time scale over 10 kilometer scale size. That kind of really dynamic structures are going on. And that creates some ups and downs of optical emission. And that seems like a true picture of the Steve. And it's also not really correct to think that these are kind of quasi-periodic wave pattern. If we make a slice along a certain line and create a power spectrum, this is a little more scientific. So let me just say a key point here. So this is telling us what wavelength structures are most dominant. So the spectral peaks, the ups and downs here means what kind of wavelengths are dominant in this data. So what this tells us is that somewhere around 10 kilometers, 20 and 30 kilometers of structures are really dominant. But the ups and downs are really small. This is pretty much characterized by this what is called the power law. So this is a really broad spectrum of intensity structures that characterize the emission structures. So this is typically seen when we see some turbulent structures. Like the flows, in the river or oceans, they are not really periodic, but all sorts of, wave period and wavelengths exist. That kind of combination characterizes the Steve emission as well. And those have been compared to, specific theories like the ionospheric feedback instability theory by Evgeny Mishin. So those things can explain why some spectral peaks exist around 10 kilometer scale size. And also the spectral slope tells us there's some shear flow instabilities going on. So these fine scale observations really helped us discussing the potential physics behind the creation of the Steven mission.
Toshi, could I ask a question on that?
Sure.
I guess this is just minor, but when you say here the 1 to 10s of kilometers of wavelength, you're talking about this range. Oh, sorry. Maybe you can't see my cursor.
So yeah, 1 to 10s and somewhere around here. So I didn't mention here, but there's a little bit of enhancement over here as well. So the gray line is a background. The black line is a stable mission. So there's about factor 2 enhancement up to here as well. And then after that, it becomes super noisy. So this is around the kilometer scale size. This is around 10 kilometers. So they are the wavelengths that showed up in their simulation. So, and they also saw some turbulent structure rather than some sort of resonance. So in terms of how this can be created, it can be because of RFM waves going back and forth, and creating the energy cascade from large to small wavelengths.
Did you have a question?
I had a similar question.
Oh.
What are those minor peaks that we are seeing?
Okay, yeah, it's a great question how these specific wavelengths, wave periods turn on. So that really depends on the density structures, but according to their explanation. So this is set up in a region called arsenic resonator. So depending on the plasma density, how fast arsenic waves can go back and forth will change. So there will be some specific frequencies or wavelengths that become brighter than the other. But it's not entirely clear why there are 3 instead of 1. I don't think anyone has an explanation at this point. But in any case, some enhancements around 10 kilometer-ish scale size and the broad spectrum from 1 to 10 kilometers. Those are consistent with their theoretical expectations. The other thing maybe I can say is that if the turbulence is fully set up, we would expect a power law. But if the turbulence is not in equilibrium yet, there will be some, active energy transfer between some wavelengths to other wavelengths. So the presence of these peaks may, indicates that, this is a, still the developing turbulence, not saturated yet. Yeah, so this may be related to the, the scale size of energy input to the system.
Toshi, Francesca,
Hi, Francesca.
did you apply any kind of windowing when you perform the power spectrum, or is it just the Fourier transform of your intensity?
This is a simple Fourier transform. There's no windowing.
Can we call those minor fluctuations as internal modulations, or
Yeah, they could be internal modulations. So these ones characterize these major structures, but because the wavelength is not constant, that's why these are broken up into multiple peaks. So probably if you look at some shorter period of time, one wave is more dominant than the other. All right. So the study we have done was based on Alan's measurement, where we're pretty much underneath Steve, but ultimately we need to understand the 3D structure of a mission. This is a 4K video by Justin Anderson. In this case, we're looking from the side, so we can see a vertical structure of Steve. And sure enough, in his video, we see very beautiful fine scale structure of Steve. So, these structures can be characterized as some, columns of emissions, and they move, along the arc. And you can sort of see that some, columns are propagating faster than others. So, this also indicates some, velocity variations, just like we have seen through Alan's video. And this is a different event, August 30th, 2022. And there's another video by Paul Smith, who has also shown a similar fine scale structure looking from the side. So there aren't many 4K videos at this point, but 3 videos showing similar things. So that gives us a hint that this kind of fine scale structure is pretty common, and they may be the fundamental steel structures that we couldn't see before due to the long exposure. But by cranking up the time resolution, just like Alan said, we just couldn't see them before, but they are the elementary structures, Steve. We need to see them, and we need to understand them in order to determine the chemical reaction or plasma dynamics that creates a stable emission. And we also have some collaboration work going on with Mark Honekel, who is an expert of determining height profile of Steve. With his analysis of the height profile, we're hoping that we can characterize the 3D structure of Steve. That's also important for understanding what kind of chemical reactions are important. Yeah, okay. So in summary, again, the citizen scientist observations were super important for enabling this research. So I'm thankful to Alan's contribution for that. This 4K video provided a way for us to do remote sensing of the dynamic multi-scale structure that happens in the mid-latitude ionosphere. Even if we have satellite observations, we have no way of seeing this kind of two-dimensional distribution of the emission structures. So this is probably the best best way to see the two-dimensional or ultimately three-dimensional structure of the ionosphere. So previously, the nitrogen has been considered as an important constituent for this emission, but the existing theory has a lot longer time constant of emission. We need to come up with a new idea to explain this kind of fast varying small scale emission structure. So that's a new contribution from this research. And again, seeing this kind of thing at high time resolution is critically important. Following up what Alan has said, I also have some suggestions to citizen scientists. So, firstly, that I should emphasize this. Anything the citizen scientists have could be really variable. Those have been already demonstrated through past researches by various people in the scientific community. And by working together between citizen scientists and scientists, we can probably do even better. So I have listed some specific suggestions. Firstly, if possible, please make images available so that we can see what you have. And you don't need to put everything. They can be just some sample images with watermarks to make sure who owns the images. They don't need to be from professional cameras. iPhone cameras can take great pictures too. And this is important. Please put the date, time, and location of the images so that retrospectively we can see when those are taken, under what conditions, and rather than saying this was taken last night, please say this was taken August 8th, 2022, something like that. And also please update your camera clocks so we know the time accurately. This is important information for us to know what happened at what time. Alan has already mentioned that. A series of images are important. One image is very variable, but oftentimes scientists want to know how things changed over time. Videos are very appreciated. And citizen scientists usually want to move cameras from one direction to another to keep chasing the most interesting things. But from scientist point of view, the fixed field of view with fixed diazo and other camera settings are important, so we can see the time series. Of course, depending on your interest, it's not going to be easy to do all these. But if we can, at least anyway, scientist point, viewpoint for so for citizen scientist images, if there's some ways to make images better, then there may be more opportunities for doing great science, between citizen scientists and scientists. And that's all I have. Thank you.
Thank you so much, Toshi and Alan. Really great presentation. There are a number of fantastic questions in the chat. And actually, Jeremy, if you're able to speak, I know you have a few of them. Maybe we could start with you.
Oh, thank you. Yes, that was a wonderful presentation. I really appreciate the insight into the capture process, the best practices for photography for citizen scientists, and then what's possible with the analysis of those images. I guess one question I was kind of thinking of was that this list in the comments was, I know there's astro-modified cameras where the infrared portion of the sensitivity in a consumer camera is generally removed, but an astro-modified camera that can be restored somewhat. So is there an advantage for Aurora citizen scientists to use an astro-modified camera that has that extra IR sensitivity? And the second question, oh, sorry, thanks. That would be my question.
Okay. Yeah, thank you for that question. Yes, the information at different wavelengths is really important for narrowing down potential chemical reactions, because the emissions have strong wavelength dependence. For Steve, it's more like the continuum emission, while auroral emissions come at particular spectral lines. So usually it's really hard to ask citizen scientists to have some filters in front of cameras, but if you have some specific cameras that can see infrared or some specific wavelengths, they are really unique. Even in the scientific community, there aren't many cameras that can see infrared emissions. Yeah, I'm sure those are really useful for doing research.
Jeremy, did you want to ask your other question also? Or one of them about having pairs of cameras or?
Oh, thank you. Yes, I understand one citizen's, you're mentioning the 3D structure of Steve, and I was just thinking about the concept. I think Mike is working on this too, but the idea of having multiple calibrated cameras in vicinity so that they could provide some kind of triangulation or stereo imaging to provide altitude data. Is that something that would be of use?
Yes, definitely. So yeah, what's missing at this point is a simultaneous measurement with this kind of side view and this kind of view from the bottom. So that if there are ways to get to measurements simultaneously, that's gonna really tell us the 3D structure. So this needs the coordination between citizen scientists. So if we can form some sort of campaigns, spontaneous drawings, in some planned fashion, yeah, hopefully with cameras at similar exposure and similar ISO setting. I know it's not easy to ask that kind of things in advance, but if there can be some coordinations done among citizen scientists that may vastly increase the amount of information we can get and can solve the questions, major questions we have in the scientific community.
Thank you very much. That was a wonderful presentation. Thank you.
Thank you.
And Sorry, just further to Jeremy's question on the modified cameras. There are a couple kinds of astro-modified cameras. Some, in fact, remove the IR cut filter entirely, so the camera is sensitive to infrared for those that like to do infrared photography. But many of the astro-modified cameras still have an IR cut filter in. They are more sensitive to the visible red H alpha for deep sky photography, but they're still cutting out infrared. So you may have an astro modified camera that may not have much benefit to bringing in their infrared wavelengths that Toshi's saying might be valuable. So you'd have to have a full spectrum, what's called a full spectrum modification, to also pick up the infrared to perhaps be of additional value, I would think, for this kind of observation.
Great. Thank you for adding that. Justin's iPhone is also asking, what about having an astro-modded camera and a non-modified camera side by side? Would that be useful? I imagine definitely yes, because we, then can compare the two. And especially as Toshi said, those observations are very rare, and I don't know what we would get. Toshi, maybe you want to expand on that. Sorry, I didn't mean to answer that, but yeah.
Yeah, I mean, knowing the wavelengths characteristics, we can narrow down to potential chemical reactions. So how much infrared emissions to be there, can be, very important for constraining, the contribution of nitrogen versus oxygen, for example, or what state of, excitation is required to create that kind of emission. So certainly, measurements, that's, broader wavelengths or certain wavelengths, will provide more information.
Yeah, that's an excellent point.
If I could just play off Jeremy's question again. By the way, Toshi, that was a wonderful presentation. Really enjoyed it. And Alan, your stuff was really illustrated the points well. Just a quick question on the depth of Steve. You can see it has the vertical structure, which really shows up nice. Do we know the approximate top and bottom of Steve? How many miles deep or kilometers?
Yeah, so there have been some triangulation research without high time resolution, and typically this emission happens between 130 and 200 kilometers. The picket fence is down below, like 110 kilometers.
Pardon me, Toshi, how far below is the picket fence again? I missed that.
How far below the picket fence? I think they can go down to like 100 kilometers or some. Perhaps Michael knows the answer better.
About 100, yes.
About 100.
And the upper part, mixed up with the whitish part, so the picket fence can reach heights above 130 kilometers. But
So
it depends on the event. It's not always the same. What is more or less always the same as the lower limit of the picket fence is always in the range of about 100 kilometers, but the upper height depends on the event.
Okay, so it can blend into the Steve portion if it reaches a very high altitude.
So the greenish part can change to white.
Change to white. Oh, great. Thank you, Michael.
I have one further comment to one question. I think it was not answered. There was a question for the camera spacing for triangulation. So I would suggest to you to separate cameras at least 50 kilometers away from each other. So having a closer spacing could be difficult for triangulation, but it also depends on the position of the triangulated structure relative to the camera. But 50 kilometer, I think it is a good separation or more.
Yeah, we're talking about emissions at 100 to 200 kilometers up. Yeah, so a similar horizontal separation, 50 or 100 kilometers would be a good length.
Vincent, do you want to ask your question? Are you able
Sure.
to?
Yep. My question is, do you think there are smaller scale structures that could be revealed by using like a longer focal length lens so you could zoom in more and see even finer scales? Or do you think that this is sort of the limit of what's supported by the physics, these scale sizes?
Yeah, so right, there can be even smaller scale structures. Based on this observation, probably we're almost seeing the limit, but there can be some additional physics going on if we go even shorter wavelengths, like ion scale size. That's the scale size where the kinetic energy exchange happens. So like Farah-Brunnerman instability can create the dissipation. So yeah, I don't know if we can reach meter scale size through ground-based imaging, but if we can, then there could be the different spectral peaks going on.
I was also wondering, since you see this, Steve, drift further south as well during the event,
Right.
it might be possible to see that turbulence change or, dissipate more later in the event.
Yeah, the time evolution of the wavy feature is something we haven't seen yet. That requires a longer longer period of observation. The Alan's video is taken for 10 minutes, and it's already a huge amount of data. So that brings the data storage issue. But suppose we can do and with triangulation, then we'll be able to see how the wave structure changing over time. That the spectral slope should be changing over time. If the turbulence is actively developing, the spectral peaks should also go up and down. We can't do that from a single location because the arc stays over the zenith for just a short period of time. So actually, this analysis was only done for like 2 minutes of data, I believe. That's because after that, the arc goes significantly away from zenith, so we can't assume that the structure we see are very horizontal. But with multiple cameras, we can avoid that kind of issue. So yeah, that's future campaigns that we may be interested in considering.
Yeah, lots of ideas for future observations and campaigns here. Any other questions out there that we missed or that folks have been holding in that they want to get in?
I just had another question about the speed. Whether the speed is fairly constant, or have you noticed any sort of periodic type variation in the speed of those raylets in Steve?
Right, the speed is definitely not constant. Even over 10 or 20 seconds of duration, the speed is going up and down quite a bit. And over 2 minutes of time scale, the speed is slowly going up. It's around 8 kilometers per second or so. Here, it's more like 9 kilometers per second. So the overall speed is changing a lot as well. So that really means that the forcing from high up in space is not constant, but varying very fast. The ionosphere conditions are changing really fast. With short exposure, we can see that dynamic interplay.
Thank you.
Great.
I have a question to the experts here. What forces are at work driving that east to west flow? Steve always goes east to west. What's Steve trying to get to going west? And have we any reports, and I guess Michael will be the best one, of a Steve after local magnetic midnight of it going the other way, west to east at all? It's always been east to west in all the Steves that I've seen and know about. So what's making it move that way, and can it go the other way?
So in this region of the ionosphere, the plasma flow is almost always from east to west, and there's a reason for that. The magnetosphere creates the the so-called electrical current system that requires plasma flow to be in that way. So the source is in the night side magnetic tail, far away from the Earth, and that plasma has to go toward noon. And so Steve is within that flow channel, so that's why it's from east to west. Whether this can reverse is an interesting question. If this happens after midnight or near midnight, there's a chance that the mission goes the other way around. We have seen proton aurora going the other way around near midnight. So in principle, it's possible. Whether a strong plasma stream that is able to create Steve can form there is a interesting question that no one knows what the answer will be.
So there's one for us citizen scientists. There's a challenge, is to keep shooting Steve and see if we can catch a late appearing Steve and going the other way. Because I've certainly seen auroras before midnight going east to west and then reverse their flow west to east. So I just wonder if the same forces would affect Steve.
You want to
I've not seen any Steve that moved from west to east. There's one exception, one case I've seen where Steve shows large-scale turbulent structures where for some moments Steve locally seems to have chaotic flow direction. So not only to the west, also to the east, but not in a let's say stable development. If you like, Toshi, I can send you a link to this event and then some images.
Yeah, sounds good. Thank you.
I've shown this event on my European Space Weather Week poster in 2019, but I did not find time to analyze it in detail. But yeah, there's one case, I think.
I've never, in all the Steves I've seen, I've never seen one after midnight, if I recall correctly. They always seem to be in the evening hours.
Right.
Have pre-dawn Steves even been observed?
Yeah.
They have. Okay. Well, I guess I got to get up, stay up a little bit later than normal to see those guys.
I think the most reports are from pre-midnight, just because most observers are out there at that time, and then not early in the morning, and it's 3 or 4 o'clock. Most people are getting to sleep earlier. So there are a few cases where Steve was observed in the early morning. Yeah, but most observations posted are.
It's uncommon. It's less common strictly due to observational bias, or is it actually
observational bias? Yeah, it's really difficult to say what is the real occurrence rate for this early morning Steve, based on citizen science observations, because you have a strong bias. Yeah.
So Michael, just to continue the question. So if it is observed in the morning, it still flows to the west. Do we know that?
In all cases, at least in all cases I have seen.
Okay. Thank you.
It's definitely expected to be in the pre-midnight time period. And, in this flow channel, since it's associated with the subauroral ion drift, that's typically where those are observed. And there might be a few edge cases where the boundaries are kind of pushed a little bit, but it would be there might be there's always some weird events. Sometimes we learn something from the weird events, but sometimes you don't necessarily, you learn that's a weird event. But yeah, okay. And then Rocky, yeah, thanks. There's also, I think, some cases where, especially when it's first appearing, it could appear to come from the west first and then go to overhead, but it's still flowing to the west. And so I'm not going to call that an optical illusion, but there's some differences in that. But yeah, like to look at that also. Okay. Thank you all so much. I am sure that we could continue talking, and there are many people very interested in this topic. I can tell by everyone on the call here today, and you all have really made some wonderful contributions to the study of Steve. I was actually talking to a scientist who is a psychologist, and he studies smoke, and they have predictions of smoke with citizen science. But he was interested in auroras and, you know, kind of like the psychology difference there of like how we might think about getting people to use his app. It's called Smoke Sense. But he was very interested to learn that his name is Steve. And so he was very interested to learn there's an aurora named after him. So that's always fun.